Yeah, good evening, children. Good evening. Good evening, online students. Anirudh, Anugraha, Kritika, and Swati.
Good evening, ma'am.
Hi, good evening. I've shared my screen. Visible?
Yes, ma'am.
Okay. All right. Fine. So today is the first class, and we are starting off with the portions for Standard 9, the first chapter in your NCERT textbook, number systems. All right. So before we get into the chapter, we'll recall some, basic terms pertaining to this chapter, number systems. As you can see on the screen, natural numbers, whole numbers, integers, and so on. So starting with natural numbers. What are natural numbers? Counting numbers are called natural numbers. Correct? Counting numbers are called natural numbers. And how do you represent natural numbers? N is equal to, N is the letter. 1 second, children, 1 second. Yeah. So counting numbers are called natural numbers. Natural numbers are represented by the letter N, capital letter N. Okay, so how do you represent it? N is equal to the set of all numbers starting from 1. Goes on. The smallest natural number is 1. The smallest natural number is 1. The largest natural number, it goes on forever. You can't say. Correct? The largest natural number you cannot say, but we know the smallest natural number is 1. And this is how you represent natural numbers. N is equal to, N is the letter that represents natural numbers. Okay, capital letter N, not small letter n, capital letter N is equal to, open a flower bracket, start from 1, 1, 2, 3, goes on and close the flower bracket. Okay, whole numbers, natural numbers including 0. Natural numbers including 0 form the collection of whole numbers. We know all this. So whole numbers are represented by the letter W, capital letter W, and it's presented like this. W is equal to, starting from 0, 1, 2, 3, it goes on like this. Whole numbers. Integers. Integers are the collection of all natural numbers, their negatives and 0. Listen to me carefully. What are integers? Integers are all natural numbers. Okay, so look at the screen there. Look at the board, all of you. All natural numbers, 1, 2, 3, 4, 5, goes on like this. Their negatives, meaning -1, -2, -3, -4, and so on. Including 0. Including 0. The collection of all natural numbers, the negatives of all the natural numbers, along with 0, form the collection of integers. See, it may be very simple, but you see, we may go wrong. When I ask you some questions, you will see yourself that the easiest of things also we can go wrong. Okay, so what are integers? Integers are all natural numbers. So 1, 2, 3, 4, 5 goes on like that, all natural numbers. Their negatives, the negative of 1 is -1. The negative of 2 is -2. The negative of 3 is -3. So it goes on. It goes on. Including 0 forms the collection of integers. So this one, it goes on, children. I'll change this. It goes on like this. All right. So integers, the collection of all natural numbers, the negatives of all natural numbers, and 0 form the collection of integers. All right. Integers are represented by the letter I or Z. I or Z. Capital letter I or capital letter Z. So you do not know. You don't know the smallest integer either. You do not know the smallest integer. Which is the smallest integer? No. The smallest whole number is 0. The smallest natural number is 1. The smallest integer you can't say. You don't know the smallest integer, so you don't know because you don't know where it starts from. See, can you see the dots? Can you see the dots? So we don't know. It starts from nowhere. Then we are here in 4, -3, -2, -1, 0 again, 1, 2, 3, 4. It goes on. So you cannot identify the smallest integer or the largest integer. You cannot. Correct? Yeah. Is this fine, children, so far? Integers, all natural numbers, their negatives including 0 form the collection of integers. This one is a mistake, children. I'll correct this. It goes on. Okay. I'll share. You don't have to write anything in today's class. Don't write anything. Next, rational numbers. Rational numbers. What have we seen so far? Natural numbers, whole numbers, integers. Natural numbers, whole numbers, very easy. You cannot forget it. But integers, sometimes you get confused with integers and rational numbers. All right. So what are integers? When we talk about integers, these numbers should come to your mind. When we say integers, you must think of all the natural numbers, their negatives and 0. That's all. When you hear the word integers, what should come to your mind? All natural numbers, their negatives and 0. 1, 2, 3, 4, 5, -1, -2, -3, -4, -5, 0. Only this collection is the collection of integers. Now, rational numbers. Integer upon integer is a rational number. The simplest way of remembering. The simplest way of remembering is integer by integer is a rational number. Okay, any expression of the form P by Q, any expression of the form P by Q, where P and Q are integers and the denominator Q is not equal to 0 are called rational numbers. You listen to me. What are rational numbers? Any expression of the form integer by integer. Integer by integer is a rational number. Simple way of remembering. When I say integers, you must think of natural numbers, their negatives and 0. They are the collection of integers. When you hear the word rational numbers means integer by integer is a rational number. Integer by integer. If the numerator is an integer, if the denominator is an integer, then that expression is a rational number. That's all. And you know what integers are. To understand rational numbers, you should understand integers clearly. Because what is a rational number? Integer by integer is a rational number. Integer, numerator should be an integer. The denominator also should be an integer. So integer by integer is a rational number. Now the numerator integer can be 0, but the denominator integer should not be 0. Because division by 0 is not defined. Division by 0 is not defined. What is 5 by 0? Let's divide 5 by 0. Am I audible, children? Online students? Anirudh, Anugraha, all of you? Am I audible?
Yes, ma'am.
Anirudh? Okay. Kritika and Swati?
Yes, ma'am.
Okay. Now let's divide 5 by 0. Okay, I'm going to divide 5 by 0. 5 divided by 0. Okay, so the numerator is always the dividend. The denominator is the divisor. The numerator is the dividend. Always. It's not that the bigger one is the bigger one is the dividend, the smaller one is the divisor. No, no. The numerator is the dividend. The denominator is the divisor. Now let's divide. 0 ones are 0. 0 twos are 0. 0 threes are 0. 0 fours are 0. But you try this one, you try this one. That is 0 by 5. 0 by 5. 0 by 5. Let's try to divide 0 by 5. So 0 is the dividend, 5 is the divisor. So 5 zeros are 0, remainder 0. Finished. See, 5 ones are 5. 5 ones are 5. What did we do? We're trying to do this one, okay? We're trying to do this. So this is the dividend, this is the divisor. 5 ones are 5. 5 zeros are 0. So we finish the division. Remainder is 0. So 0 by 5 is defined. 0 by 5 is 0. Numerator can be 0. Denominator should not be 0. Why? Because as we just saw, if the denominator is 0, 5 by 0, anything by 0, see, not 5 by 0, anything by 0. So 11 is the dividend. 0 is the divisor. 0 into anything is 0. So you cannot complete this division. So 11 by 0 is not defined. Division by 0 is not defined. See, when you divide, you must get unique answer. When you divide, okay, now I think some of you are still confused, like why is this lady saying this? Let me tell you why. Because when you divide two numbers, the answers are unique. When I say the answers are unique, meaning when you divide two numbers, you get a unique quotient and remainder. When you divide a number by another number, you will get a unique quotient and remainder. But for this, the quotient will be the same. Supposing, 5 by 0. So you feel 0, 0, zeros are 0. Complete the division. Remainder is 5 again. How can you get the dividend itself as the remainder? We never get the dividend itself as the remainder. You'll get something less than that, right? Okay. Now, again, another reason is because the quotient is not unique. Now you try to divide 7, 0 zeros are 0, 7 is the remainder. You're getting 0 only as the, when you divide 7 by 0, you're getting the same quotient 0, which means the quotient is not unique. You're getting the same 0 for different divisions. Yeah, so division is not unique. And that's why division by 0 is not defined. Okay. So integer by integer is a rational number. The numerator integer can be 0, but the denominator integer should not be 0. That is a rational number. Okay, so how do you define a rational number? Then the numbers of the form P by Q, where P and Q are integers and the denominator Q is not equal to 0, are called rational numbers. Okay, and a rational number will either have a, okay, we'll come to that later. All of you understood rational numbers? Online students? Integer by integer is a rational number, understood?
Yes, ma'am.
The numerator, can the numerator be 0?
No, ma'am.
Who said no? The numerator can be 0. Which one should not be 0?
The denominator.
The denominator should not be 0. Numerator can be 0. The denominator should not be 0. Now answer this question. Anirudh? Anirudh?
Ma'am.
Is -3 an integer?
Yes, ma'am.
Yes. Anigraha? Is 0 an integer?
Yes, ma'am.
Swati? 5 by 2 is an integer?
No, ma'am.
Why? Because 5 by 2 is not an integer. Why? Because it's not in that collection. See, when somebody asks you, is this an integer? What will you think? Is it a natural number? No. Is it the negative of a natural number? No. Is it 0? No. Then it's not an integer. Integer can be any one of these three. Integer should be any one of these three. If somebody asks you if this is an integer, what will you ask yourself? Is it a natural number? Is 5 by 2 a natural number? No. Is it a negative of a natural number? No. Is it 0? No. What is an integer? An integer is a natural number or the negative of a natural number or 0. 5 by 2 is not any of it. So 5 by 2 is not an integer. 5 by 2 is not an integer. Now 5 by 2 is a rational number. Why is 5 by 2 a rational number? Because the numerator is an integer, 5. The denominator is an integer, 2. 5 is an integer. 5 is an integer, correct? And 2 is also an integer. And integer by integer is a rational number. What about -5 by -3? Is -5 an integer? Yes. Is -3 an integer? Yes. So is this integer by integer? Yes. It's a rational number. It's a rational number. Of course, you can cancel minus and minus. It's a rational number. Now tell me, is minus 7 a rational number? So when somebody asks you, is it a rational number? What should you ask yourself? Is the numerator an integer? Is the denominator an integer? If it is yes, it's a rational number. Is the numerator an integer? So it's not in the fractional form. So put a by 1. By 1. Is the numerator an integer? Yes. Is the denominator an integer? Yes. So it's a rational number. Minus 7 is a rational number. Minus 7 is an integer. Minus 7 is also a rational number because minus 7 can be written as minus 7 by 1. Where minus 7 is an integer, 1 is also an integer. And since it takes the integer by integer form, it is a rational number. Kritika, is 3 a rational number?
No, ma'am.
Anugraha, is 3 a rational number?
Yes, ma'am.
Why?
Because we can write 3 as 3 by 1 and fractions will come under rational numbers.
You should not. What did I tell you? What is a numerator? It's an integer. And what's a
Yes.
denominator? It's an integer. Integer by integer is a rational number. So if you don't see a denominator, you can always use 1. You cannot use it. You cannot use 2. You cannot write 3 as 3 by 2. There is no denominator. So let me write, 3 as 3 by 2. That you cannot do. You cannot say 3 does not have a denominator. So let me take 2 as a denominator. No. 3 by 2 is not 3. 3 by 1 is 3. 3 by 1 is still 3. If you write 3 by 2, 3 by 2 is not 3. 3 by 2 is 1.5. You're changing its value. Correct? So you can always give the denominator as 1. If that expression does not have a denominator, you can always take 1 as a denominator. Correct? Now tell me, is 10 a rational number? So it does not have, see, rational number. Immediately, integer by integer. So by integer illa, so put a by 1. Now 10 is an integer, 1 is an integer. So this is a rational number. So 10 is a rational number. 10 is a rational number. 0 is a rational number because 0 can be written as 0 by 1. 0 is the only number which can be written with any denominator. 0 is the only number. Now see, if you take 10, you can write 10 as 10 by 1, but you cannot write 10 as 10 by 2 because 10 by 2 is a different number 5. You cannot write 10 as 10 by 5. 10 by 5 is a different number 2. But if you write 10 as 10 by 1, 10 by 1 is still 10 only. You can give a denominator so that the value still remains the same. The value should not change, right? So 10 can be treated as 10 by 1, which is integer by integer. So it's a rational number. But if you take, now you cannot write 10 as 10 by 2. But in the case of 0 is a rational number because 0 is 0 by 1, 0 is 0 by 2, 0 is 0 by 3. 0 is the only number that can be taken with any denominator because 0 by 1 is 0. 0 by 2 is also 0. 0 by 3 is also 0. So 0 can be written in many ways. 0 can take any denominator. Division by 0 is not defined. Don't take 0 by 0. Other than that, 0 by 1, 0 by 2, 0 by 3, everything is 0. Agree all of you? 0 alone can take different denominators. You can treat 0 as 0 by 1 because the value is still 0. You can treat 0 as 0 by 2 because the value is still 0. Okay, so 0 is a rational number. 0 is a rational number because 0 is 0 by 1 or anything 0 by 2, integer by integer. So it's a rational number. Yes or no? Yes. But if you take 7, 7 is 7 by 1 only. 7 is not 7 by 2. 7 is 7 by 1 only. And that is integer by integer again. So it's a rational number. So with this, you can conclude, or we can conclude that every natural number can be written with denominator 1. So it's a rational number. Every natural number, online students, every natural number, 1 second. Yeah, actually, this bad throat, Yeah, I think it'll take some time, then I'll get back my voice. So I was telling you that every natural number, see here, 1, 2, 3, 4, everything can be taken by 1, correct? Everything can be taken by 1. So everything is a rational number. Every whole number can be taken by 1. So it's a rational number. Every integer can be taken by 1. So rational number. Which means every natural number is a rational number. Every whole number is a rational number. Every integer is a rational number. Correct? Because every number can be given the denominator 1. And so every natural number is a rational number. Every whole number is a rational number. Every integer is a rational number. Correct? Okay. But all rational numbers are not natural numbers. The other way is not true. Now 5/2 is a rational number because integer by integer, but it's not a natural number. 5/2 is a rational number, but it's not a whole number. 5/2 is a rational number, but it's not an integer. The other way is not true. The other way is not true. -3/4 is a rational number because integer by integer, it's a rational number, but it's not a natural number. It is not a whole number. It is not an integer. Why is it not an integer? Because it's not an integer because integer must be a natural number or the negative of a natural number or 0. Integer should be what? It should be a natural number or the negative of a natural number or 0. So it's not that. So it's not an integer. Clear, all of you? So do not get confused with these 4 terms. Natural numbers, whole numbers, integers, and rational numbers. Yes, now, Anirudh, true or false? Anirudh, say true or false. Every rational number is an integer.
No, ma'am.
Give an example. Give an example to justify your answer. So like you must say, this is a rational number, but it is not an integer, like that.
Minus 7/3, ma'am.
Okay, -7/3 is a
Rational number, but it is not an integer.
That's not an integer. Correct. Very good. -7/3 is a rational number because integer by integer is a rational number. Correct.
Yes, ma'am.
So yeah, -7/3 is a rational number, but it is not a integer. So every rational number is not an integer. Very good. Anugraham. Every whole number is a natural number.
False, ma'am.
Why?
Ma'am, because 0 is not a natural number.
Correct. Every whole number is not a natural number because 0 is a whole number, but it's not a natural number. See, when you say true, it should always be true. Otherwise, it's false. When you say true, it's always true. So every whole number is a natural number, is a statement. 0 is a whole number, but it's not a natural number. So the statement is false. Kritika. Sorry. Every natural number is a whole number. Kritika. True or false? Swati,
Ma'am,
every natural number is a whole number, true or false? Sorry?
it's true, ma'am.
It's true. Every natural number is a whole number. Take any natural number, it is a whole number. So this is true. So what are rational numbers? Again, what are rational numbers? Integer by integer is a rational number, where the denominator should not be 0. Very good. But how do you really define a rational number? An expression of the form P by Q, an expression of the form P by Q, where P and Q are integers and Q not equal to 0 is called a rational number. It's called a rational number. If you can, I can't see it. But yeah, it's called a rational number. Correct? Integer by integer is a rational number. And what is an integer? Integer means all natural numbers, their negatives and 0. Integer means all natural numbers, their negatives and 0. This collection forms integers. All right. Okay. Now coming to the actual 9th standard. What are the decimal? Now when we say rational number, it has a P by Q form. When we say rational number, it has a P by Q form. That means you can divide. Division is possible there. Division is possible. Now when you divide, there are only two cases. Either the division can come to an end with a 0 remainder, or the division goes on and on. When you divide the numerator by the denominator, because we said rational numbers have a P by Q form, right? So when they have a P by Q form, that means it's possible to divide the numerator by the denominator. Now when you divide, two things can happen. Either the division comes to an end with a 0 remainder, or the division goes on and on. When the division comes to an end with a 0 remainder and you look at the quotient, it'll be a terminating decimal. If the division does not come to an end, the division goes on forever. Then if you look at the quotient, you will have a non-terminating repeating decimal. Okay, let me show you some examples. Just wait 1 second. Sorry, 1 second. I'll just find it. Okay, I haven't still made those presentations. Fine. Those presentations are still not ready. So now I'll just tell you orally. I'll show you the results in the next class. So when you divide P by Q, okay, when you divide P by Q, so supposing you divide, say 15 by 3. What happens when you divide 15 by 3? The division comes to an end with a 0 remainder, and the quotient is a terminating decimal because 5 means 5.0. The terminating decimal. Now divide, say 16 by 3. 16 by 3. Okay. When you divide, see again, it is integer by integer. Integer by integer. It is a rational number. Okay. So we are dividing 16 by 3. 3 5s are 15. 1 remains. Then keep a point, add a 0. 3 3s are 9. 1 remains, add a 0. 3s are 9. 1 remains, add a 0. Don't you think it goes on and on? Can you complete this division? Will this division come to an end with a 0 remainder? No, it goes on and on. And what's the remainder? 1. 1 is a remainder in every step. And what is that digit which is happening in the quotient? 3. You're getting 1 remainder, 3 in the quotient. 1 remainder, 3 in the quotient. 1 remainder, 3 in the quotient. So this is a case where the division does not come to an end. And what is happening is you get one remainder repeats itself. When one remainder repeats, there will be one digit in the quotient that will keep repeating itself. If 2 remainders repeat, then 2 digits in the quotient will repeat. If 3 remainders repeat, 3 digits in the quotient will repeat. I'll show you the examples in the next class. It will be more clear. Now just take it because I don't want to spend time dividing and showing the result. Division itself is going to take time. So just understand theoretically now. When we divide, that is when you have a rational number, when you perform the division, two things can happen. The division comes to an end with a zero remainder, or the division does not come to an end. The division goes on and on. So either one, you keep getting the same remainder, one remainder, or you may get two remainders repeating itself, three remainders repeating themselves. So if three remainders repeat, you will see that in the quotient, you will get the same three digits repeating themselves. So this is the case where the quotient will be a non-terminating but repeating decimal. Non-terminating repeating decimal. Which means if it is a rational number, only two things are possible. When you have a P by Q, only two things are possible. When you divide P by Q, the division comes to an end with remainder 0. And when you see the quotient, it will be a terminating decimal. See, the quotient can be 20, meaning 20.0. What do we mean by terminating decimal? That's it. Terminates, meaning it ends somewhere. Now, the other cases, you divide and the division goes on and on. You don't get zero remainder. And what do you observe? Either one remainder keeps repeating or two remainders. Like you get 9, 8, 9, 8. You keep getting the remainders 9, 8, 9, 8, 9, keep getting it. So when those remainders 9, 8 keep repeating, you will see that in the quotient, some two digits, it need not be 9 and 8 in the quotient also. Some two digits in the quotient also will keep repeating themselves. Supposing you have remainders like 1, 5, 4, 3 and 2. 1, 5, 4, 3 and 2. 1, 5, 4, 3, 2. When you divide, you'll get the same remainders. 1, 5, 4, 3, 2. Again, 1, 5, 4, 3, 2. 1, 5, 4, 3, 2. So these five remainders will keep repeating. And if you see in the quotient, some 5 digits, it need not be 1, 5, 4, 3, 2. Some 5 digits will keep repeating themselves in the quotient. Some other 5 digits, the same 5 digits will keep repeating. So the second case is when the division does not come to an end with a zero remainder, but you see that one remainder or a set of remainders keep repeating themselves. So when you look at the quotient, either one digit or a set of digits keep repeating themselves in the quotient. Such a quotient is called a non-terminating repeating decimal. Repeating because one digit or a set of digits will keep repeating themselves. So a rational number can have only two kinds of decimal expansions. A rational number will have a terminating decimal expansion or a non-terminating repeating decimal expansion. But we have one more. Call upon check. We have one more kind of decimal. Non-terminating, non-repeating decimal. Non-terminating. Don't write anything, children. All the notes will be given to you. Don't write anything. We have one more. Non-terminating, non-repeating decimal. These are the three kinds of decimals we have. Terminating decimal, non-terminating repeating decimal, non-terminating non-repeating decimal. The first two are rational numbers. The last one is an irrational number. So what are irrational numbers? What are irrational numbers? Don't read anything more. So what are irrational numbers? Irrational numbers will not have a P by Q form. Okay, let me just write what I told you. So we were talking about rational numbers. Rational numbers, they have a P by Q form. So when you divide P by Q, remainder can be 0. If the remainder is 0, then the quotient will be a terminating decimal. Otherwise, the other cases, when you divide P by Q, the remainder is not 0. Then when you see the quotient, it will be a non-terminating but repeating or recurring decimal. Repeating or recurring decimal, both are the same. Non-terminating repeating decimal or non-terminating recurring decimal. With terminating, you don't have terminating, repeating, terminating, non-terminating decimal is only terminating decimal. Non-terminating decimal is non-terminating repeating, non-terminating, non-repeating. So basically two kinds of decimals, terminating, non-terminating. Terminating is terminating. Non-terminating is non-terminating repeating, non-terminating, non-repeating. Or you can say non-terminating, non-terminating recurring, non-terminating, non-recurring. So the last one, non-terminating, non-recurring or non-terminating, non-repeating. When will that happen? That does not happen when you do P by Q. When we do P by Q, we get only terminating decimal or a non-terminating repeating decimal. Then how will you get this non-terminating, non-repeating decimal? That does not come from a P by Q. So an irrational number, they are called irrational numbers. So what is an irrational number? An irrational number does not have a P by Q form. A rational number has a P by Q form. An irrational number does not have a P by Q form. Okay, and so again, same thing. It does not have a P by Q form where P and Q are integers and denominator not equal to 0. It does not have a P by Q form. Then from where do we get these non-terminating, non-repeating decimals? So they are the results of expressions like √2, √3, cube root of 10. Okay, the square root of 2. When you find the square root of 2, you will see that its value is a non-terminating, non-repeating decimal. Now square root of 2. You will say square root of 2 is square root of 2 by 1. But it does not have it. This is not an integer. Square root of 2 can be written as square root of 2 by 1. So we may feel this is also like integer by integer. It's a rational number. No, it's not an integer. √2 is not an integer. You can write √2 as √2 by 1. You can write √2 as √2 by 1. But it is not P by Q because √2 is not an integer. 1 is an integer, but the numerator is not an integer. Correct? So this is not a P by Q because P by Q means integer. P by Q means integer by integer. P by Q means integer by integer. So here √2 is not an integer. Correct? Yeah. So we are talking about from where do we get these non-terminating, non-repeating decimals? The values of √2, expressions like √2, √3, cube root of 10. Now what about the square root of 25? Square root of 25 is 5. And 5 is 5 by 1. Integer by integer. This is a rational number. So square root of 25 is also a rational number. Now don't think anything under the square root is irrational. Don't think anything under the square root is irrational. No. What is square root of 100? 10. And what is 10? 10 by 1. Integer by integer. It's a rational number. So this one is a rational number. I'm not saying anything under the square root is an irrational number. So square root of 121 is 11. And 11 is 11 by 1. P by integer by integer. It's a rational number. Now supposing cube root of 27. Cube root of 27 is 3. 3 into 3 into 3 is 27. So cube root of 27 is 3 and 3 is 3 by 1. Integer by integer. Integer by integer. It's a rational number. Yes or no, class? What about the fourth root of 64? Is there any natural number when is there any natural number which when multiplied with itself 4 times produce 64? 4 into 4 into 4 into 4. How much? 4 into 4, 16. 16 into 4 is 64. 2. Is there any natural number which when multiplied with itself 4 times can produce 64? Something into 4 times. So something into something into some same thing. It is not something into something else. Okay. So something into something into something into something is equal to 64. If you put 4 here, 4, if you put 4, 4 for the 16, 16 for the 64, 64 for the 256. If you put 2, if you say 2, 2 to the 4, 4 to the 8, 8 to the 16. So 4th root of 16 is 2. 4th root of 16 is 2. All right. Now tell me 4th root of what is okay, cube root of what is 5? Cube root of what is 5? Cube root of what is 5? Yeah?
125.
125. Cube root of 125 is 5. Because five multiplied with itself 3 times gives us 125, which means the cube root of 125 is 5. All right. So now cube root of 125, is this rational or I'm answering it? I'm answering it. Is cube root of 1 is cube root of 125 rational or irrational? Is the question. Now, whenever it is possible, you should simplify. You must find the value and then you should comment. You should not look at this cube root, so irrational. No, it's not like that. Don't just see that, symbol, cube root, irrational, square root, irrational, 4th root, irrational. No, it's not like that. Can you find the value of cube root of 125? It's 5. And what is 5? 5 by 1. And what is 5 by 1? Integer by integer. So cube root of 125, though it looks like that, is a rational number. It looks like cube root of 125. It does not look like a rational number, but it is a rational number because its value is 5 and 5 is 5 by 1 and 5 by 1 is integer by integer. Is that clear? Now, when you take cube root of, say 10, anything into itself 3 times, can it produce 10? Any natural number multiplied with itself 3 times. 2 into 2 into 2, 8. 3 into 3 into 3, 27. So 10 you will not get. No natural number multiplied with itself 3 times can give us 10. So cube root of 10 is a non-terminating, non-repeating decimal. Cube root of 10 is a non-terminating, non-repeating decimal, and cube root of 10 is an irrational number. It does not have a p by q form because though you can write it as by 1, it's not integer by integer. You can write this as by 1, but this one is not an integer. This one is not an integer. It's not a rational number. Yes or no, children? So now summing up, we just understood rational numbers and irrational numbers and irrational numbers. Rational numbers and irrational numbers. Rational numbers have a p by q form, integer by integer form. Irrational numbers do not have a p by q form. They do not have a p by q form. When you divide p by q, division comes to an end, does not come to an end. When the division comes to an end, the quotient is a terminating decimal. Terminating decimal. So a rational number can have a terminating decimal expansion. A rational number can have a terminating decimal expansion. Or if the division goes on and on, the division goes on and on, then the quotient will be a non-terminating, repeating decimal. Non-terminating, repeating decimal or non-terminating, recurring decimal. Only these two are rational numbers. Which is the other one? Non-terminating, non-repeating or non-terminating, non-recurring decimal. From where do you get that? Not by division, not by dividing. When you divide p by q, because when you divide p by q, you cannot get a case like that. So what is the third one? Non-terminating, non-repeating decimals. And what are they called? Irrational numbers. Irrational numbers do not have a p by q form. And from where do we get these non-terminating, non-repeating decimals? From these values, the square root of 2, or the 4th root of 15, or the 7th root of 3. Some number multiplied with itself 7 times, it should give you 3. some natural number multiplied with itself 7 times. It should give you 3. So that this value is a non-terminating, non-repeating decimal. Is that clear? Now the collection of all the rational numbers and irrational numbers are called real numbers. The collection of all rational numbers and irrational numbers are called real numbers. What are real numbers? Real numbers are basically the numbers that exist. Whatever numbers that exist are called real numbers. Numbers that don't exist are called imaginary numbers or unreal numbers. That you will study only after 10th. Till 10th standard, we will be seeing only real numbers. That is numbers that exist. Numbers that exist. Real numbers are numbers that exist. Real numbers are classified as rational numbers and irrational numbers. Rational numbers and irrational numbers put together form real numbers. So a real number can have a terminating decimal expansion. A real number can have a non-terminating repeating decimal expansion. A real number can have a non-terminating, non-repeating decimal expansion because a real number is either rational or irrational. Every rational number is a real number. Every irrational number is a real number. Because real numbers are classified into rational and irrational. So rational, irrational both together form real numbers. The collection of all rational numbers and irrational numbers form the collection of real numbers. Real numbers are numbers that exist. Real numbers are numbers that can be represented on a number line. Every real number has a unique position on the number line. Every real number has a unique position on the number line, meaning you can represent any, see, there are infinitely many numbers. Every real number has its own place on the number line. It will not share it with anybody else. Every real number has a unique place on the number line, its own place on the number line. That's why the number line is called a real number line, because every real number has a place on the number line. So the number line is called a real number line. Real number line. All right. So what are real numbers? The collection of all rational numbers and irrational numbers form real numbers. And what are real numbers? All the numbers that exist. And every real number has its own position on the number line. Like when we were young, we have represented, no, they'll tell you show -3 on the number line. Show -3. You've learned when you were young, no? Show -3. So you'll, as a little girl or a boy, you'd have marked like this, marked like this, marked like this, and then you'll say this is only A. Correct? This is the position of -3 on the number line. Now last year in 8th standard, they'll tell you show 7/4 on the number line. So this is 0/4. Correct? Just a minute, children. Yeah, we were trying to represent 7/4 on the number line. Let me make it more simpler. 3/4 I'll make it now. 3/4 on the number line. So 0/4, 1/4, 2 by 4, 3 by 4, 4 by 4. So this is 3 by 4. Correct? This is 3 by 4 on the number line. Now supposing minus, say what, minus what? So some minus 7 by 8. So what will you do? The 0 by 8. Minus 1 by 8. Minus 2 by 8. Minus 3 by 8. Minus 4 by 8. Minus 5 by 8. Minus 6 by 8. Minus 7 by 8. Minus 8 by 8. What is minus 8 by 8? This is only minus 1. Minus 8 by 8 is minus 1. So this is minus 7 by 8. The point A on the number line represents minus 7 by 8. Correct? So we have represented rational numbers on the number line. Okay. So when you were in probably 5th or 6th, you would have represented 1, 2, 3 or negative numbers, minus 3, minus 4 on the number line. Then 7th, 8th standard, you have represented fractions on the number line like this. Represent minus 7 by 8 on the number line. Correct? So that's what. So that means what? You're trying to say that every rational number has a position on the number line. Now this year, you will also represent irrational numbers on the number line. You will represent root 2 on the number line, root 3 on the number line. You will find the position of root 2, root 3, all those irrational numbers on. So far, you have been finding the positions of only rational numbers on the number line. Now this year, you will learn how to find the position of an irrational number on the number line. That means what? In 4th and 5th and 6, 7, 8, you have represented rational numbers on the number line. Now we are going to represent irrational numbers on the number line. So that means what? Rational numbers and irrational numbers have their own positions on the number line. Correct? So that means all the real numbers have a unique position on the number line. Name any real number. It has a unique position on the number line. It won't share it with anybody else. It has its own place. Okay? So real numbers are the collection of all rational numbers and irrational numbers. Now, answer the question. Anybody online? Every real number is a rational number. True, false. Every real number is a rational number. True, false. Online.
True.
How many of you say true? How many of you say false? Name yourself.
Ma'am, Anirudhan, true, ma'am.
Anirudh, true. Then louder. Anugraha, true, false.
I'm true.
Anugraha, true. Swati, I can't call out like this quickly.
Can you repeat the question? Your voice was breaking.
Yeah. Can you see the statement?
False, ma'am.
Okay, she says false. Swati says false. Yeah, class here. How many false? Raise your hand. How many true? Not sure இருக்கு. Not sure எதுக்கும் தூக்காதீங்க கை அவ்வளவுதான். சேஃபா இருந்துக்கலாம். நீங்க for not sure. True. Yes, அழகம்மை. Yes. False. True. False. Read it once again. Real numbers na enna? Real numbers la rational irukku, irrational irukku. But you're saying every real number is only rational. What did we just understand? Real number means what does it have in it? A real number has both rational and irrational in it. But you're saying every real number is only a rational number. Then where will the irrational number go? So the statement is false. The statement is false because every real number is a rational number, meaning is only a rational number. But what did we just understand? Real number is the collection of all rationals and irrationals. So the other way is true. Every rational number is a real number. True. Every irrational number is a real number. True. This way is not true. Every real number is rational. It can be irrational also. See, real number has two things in it. Real number is rational or irrational. But you're saying every real number is only rational. But what did we understand? Every real numbers are both rational and irrational, meaning the collection. So in the statements, you need to tell yourself and get that very clear. When we say real numbers, we are talking about both rational and irrational numbers. Now the statement which I just said is every real number. Real means rational, irrational, both. Okay, rational, irrational, both are there. Every real number is a rational number. I'm saying every real number is a rational number. Every real number is not a rational number. It can be irrational also. So this is false. I hope all those who said true understand. Offline students, if you felt it was true, now do you understand it's false? Every rational number is a real number. True or false? Online, true or false? Every rational number is a real number.
True, ma'am.
True. Every irrational number is a real number.
True, ma'am.
True.
True. Yeah, every irrational number. It's like asking like this. Every tiger is an animal. Every giraffe is an animal. Every animal is not a tiger because animals are many. Like animals, it is real numbers here. Like animals, it is real number is a collection. Like animals is a collection. Tiger is only tiger. Elephant is only elephant. So rational number is rational number. Irrational number is irrational number. But what are real numbers? It's both rational and irrational put together. So like every giraffe is an animal. Every animal need not be a giraffe. Animals can be many, right? So like that. Here, every rational number is a real number. Yeah, true. Rational numbers are real numbers. Every irrational number is a real number. True. The other way, every real number is rational. Every real number is rational. So this is false because real numbers are both rational and irrational. But you're saying every real number is only rational. So this is false. Similarly, every real number is irrational. That means you're saying if you take any real number, if you pick any real number, it is irrational only. Then what about the rational numbers? Because real numbers is the collection of both. Correct? So you should not get confused, children. So first natural numbers. Then with natural numbers, if you put 0, whole numbers. With the whole numbers, if you add the negatives of the natural numbers, integers. Okay. And the next thing is rational numbers. Rational numbers are all these. Rational numbers are integers, whole numbers, and natural numbers. All are rationals. All the three. We started with natural numbers, whole numbers, integers. All these are rational numbers because everything can be by one. All are rational numbers. Then after rational, we saw something else, irrational. They both are different. Rationals and irrationals are like North Pole and South Pole. They have no similarity. They're totally two different things. Rational numbers and irrational numbers are totally two different things. This one ends. This chart ends here. Natural numbers, whole numbers, integers, rational numbers. Finished. That's all. This one is on the other side, irrational numbers. It stands alone. It doesn't come from anything. Irrational numbers stand alone. All these are real numbers. Everything are real numbers. A natural number is a real number. A natural number is a real number. Because a natural number is a rational number. Understand now? So now many statements you can make like that. Natural numbers, to that if you add 0 whole numbers, to the collection of whole numbers, if you add the negatives of the natural numbers, integers, and all these are rational numbers. Whole numbers, natural numbers, integers, all are rational numbers. And what are rational numbers? P by Q form. Integer by integer is a rational number. This is over on one side. On the other side, we have irrational numbers. Okay, now all these are real numbers. All these are real numbers. Real numbers are the numbers that exist, and these are all real numbers. So the collection of all rational and irrational numbers are real numbers. Rational numbers have only two kinds of decimal expansion: terminating decimal expansion, non-terminating repeating decimal expansion. Because when you divide, only two things can happen. Division comes to an end with 0 remainder, terminating decimal. Division does not come to an end, goes on and on forever, non-terminating repeating decimal. Then from where do we get non-terminating, non-repeating decimals? They don't have a P by Q form, not from division. We don't get that from division. Yeah, they are the values of root 2, root 3, cube root of 5. So the square root of an imperfect square, cube root of an imperfect cube, and so on. They are the values of square roots of imperfect squares, cube roots of imperfect cubes. Last year, you would have learned, na? 10 is not a perfect square. 10 is not a perfect square. So the square root of 10 is an irrational number. 30 is not a perfect cube. So the cube root of 30 is an irrational number. Okay, now I cannot stuff everything into your head today. So we'll leave it there. Now we understood something. We'll now proceed. Is it fine, children, online students? So far?
Yes, ma'am.
Yes, ma'am.
Okay. Now, no, today you're not writing anything. We're just listening today, okay? I'll share the notes with you. I'll tell you what to do. Today, don't write anything. Now, we are going to understand something different now. Without dividing, see, what can you see? You can see some rational numbers. 15 by 96, 11 by 24. You can see integer by integer. In all these, questions A, B, C, D, E, F, you can see integer by integer. So these are all rational numbers. So that means they can have two kinds of decimal expansion, either terminating or non-terminating, repeating. Now you should not divide. Without dividing, you must say, without dividing, you should say if this fraction has a terminating decimal expansion or a non-terminating repeating decimal expansion. But you should not divide. So there's a method. Without actually performing the long division, you can identify if a P by Q has a terminating decimal expansion or a non-terminating repeating decimal expansion. So for that, you must first put the P by Q in the simplest form. That's the first step. Put the P by Q in the simplest form. So simplify 3 5s are 3, 32 times, correct? Okay, so the simplest form of 15 by 96 is 5 by 32. So after putting the rational number in the simplest form, look at the denominator. Look at the denominator, 32. Express that as a product of primes. So 2 to the power 5, or you can write 2 into 2 into, see like this, 32, 2 16 times. You all know this method, 2 8 times, 2 whatever, 4 times 2, 2 times 2 ones are, you know this, right? So 2 into 2. Now, in the prime factorization of the denominator, if you see only 2 and 5, or either 2 or 5, or both, it can be only 2s, only 5s, or 2s and 5s. But nothing other than, no prime factors other than these. The prime factorization of the denominator can have only 2s, meaning 2 to the power something, or 5 to the power something, or powers of 2 and 5. Okay, so like 50. Now 32 is 2 to the power 5. Now if you take 50 or 100, if you take 100, 100 is 2 square into 5 square. If you take 1000, okay, if you take say a 200, 200 is what? 25 eights are right. 25 eights are right. So 8 is 2 cubed and 25 is 5 square. One second, children. Yeah, 200 is 2 cubed into 5 square. See how to find, you all know it. See like this, 200 times, 250 times like this. You all know this. You all know this. So 200 is 2 cubed into 5 square. So 200 is made up of only the primes 2 and 5. So like this. So if the denominator has 2 or 5 as its prime factors, then that p by q will have a terminating decimal expansion. If it has any factor other than 2 or 5, it will have a non-terminating repeating decimal expansion. You cannot get non-terminating, non-repeating here because it is p by q. P by q la non-terminating, non-repeating varave varadu. Rendu dhaan irukku p by q na. P by q means only terminating or non-terminating, repeating only. Don't bring non-terminating, non-repeating here. It doesn't come in p by q at all because they don't have a p by q form. So 15 by 96. What is the condition? You should not divide. But you must say if it has a terminating or a non-terminating repeating decimal expansion. What to do? This is what you should do. I'm repeating it. Take the given p by q. Put it in its simplest form. Put it in its simplest form. After that, take up the denominator. Express the denominator as a product of its primes. What is the prime? Only 2. So 15 by 96, when you divide, when you divide 15 by 96, the decimal expansion will terminate. So I'm doing it in the calculator. 15 divided by 92. 92 is, it's not, like, it's not showing it fully here. What is it? 5 by 32, na? 5 divided by 32. Okay. 0.15 by 96 is equal to, when you divide it, 15625. That's all. After this, the remainder would have been 0. Remainder 0 and the quotient is 0.15625. That's it. But we didn't divide. We didn't divide. Without dividing, we said that you see, the question is not what is the terminating decimal expansion. The question is, will it have a terminating decimal expansion? Yes, it has a terminating decimal expansion. The question is not what is the terminating decimal expansion. For that, you should divide. There is another method also. We won't see that this year. That is next year. For this year, it's only this much. Okay, now let me take up the next one. I'll not stick to the same thing. Now the next one, 11 by 24. 11 by 24. It's already in the simplest form. You cannot simplify it any further. It's already in the simplest form. So then you should take up the denominator 24 and express it as a product of its primes. And that is 2 cubed into 3. 2 cubed into 3. All right. 2 cubed into 3. 3. It's not 2, 5. It's something else. 3. So this, when you divide 11 by 24, the division will not come to an end with 0 remainder. So the quotient will be a non-terminating repeating decimal. 11 by 24. 11 divided by 24. 11 by 24 is, when you divide, you will get 0.4581. goes on 3, 3, 3, 3, 3. This digit 3 goes on forever. This digit 3 goes on forever. That means after some steps, you're getting the same remainder. After a few steps of division, you're going to get the same remainder like 1, 1, 1, 1, 1, 1. So 3, 3, 3, 3 goes on in the quotient. That's the indication. Because 3 alone is repeating. That means there is some remainder, some particular remainder that goes on forever. Now, okay, now let's do the next one. With that, I think you should be able to understand clearly. Look at C, 27 by 80. Is it in the simplest form? Can you simplify this any further? No. No. So take up the denominator. Do it anyways, like 16 5s are 80. So 2 to the power 4 into 5. See, now the not a 80 na simply write something. No, I'm not writing it that. 80 when you do this, 80 to 40 times, to 20 times, to 10 times, to 5 times, and 5 answer. So you can see 2 to the power 4 into 5. 2 to the power 4 into 5. So what are the primes you see? 2, 5. See how many 2s, how many 5s, that we are not concerned. Only 2 5 should be there. That's all. See here it's 2 to the power 4, but 5 to the power 1. That's okay. It's not that if it is 2 to the power 4, it should be 5 to the power 4. There should be no other prime other than 2 or 5. That is the condition. And that condition is satisfied here. There's only 2, 5. 2 more. There can be only 2, only 5, or both 2 and 5. Terminating decimal expansion. If there's any factor other than this, non-terminating, repeating decimal expansion. Is that understood? See here. So these slides I'll share with you. You should understand. And then you'll complete all this. So I'll just show you the see here. Okay, let me see the first one. How to present it. See here. 15 by 96. Just cancel. Okay, so cancel. When you cancel, you get. I cannot show the cancelling here. Okay, that's why directly you can see 5 by 32 because I cannot. When I prepare on Word, I cannot slash it like this. So this is actually 3 5s and 3 32 times. That's what you see here, 5 by 32. Write 5 as it is and 32, it's prime factors, which is nothing but 5 by 2 to the power 5. The denominator has no prime factors other than 2, correct? Therefore, 15 by 96 has a terminating decimal expansion. This is how you present it. First, put it in the simplest form, 5 by 32, simplest form. See, this cancelling only you would have cancelled. You should cancel 3 5s are 3 32 times like this. You should cancel and then you should write 5 by 32. Everywhere this cancelling alone you cannot see in my presentation because I cannot do that. That cancelling alone you cannot see, but you should cancel it. So you get 5 by 32. Now 32 like this. So the denominator has no prime factors other than 2. Therefore, the given fraction has a terminating decimal expansion. When you see the next one, it's already in the simplest form. It's already in the simplest form. So 24 is 2 cubed into 3. The denominator has 3 as a prime factor, which is other than 2 and 5. Understand? The denominator has 3 as a prime factor, which is other than 2 and 5. Therefore, 11 by 25 will not. See, you should not write has a, you should not write, if they ask you, is it sweet or not sweet? You must write it is sweet or not sweet. You must not say it is salty. Did they ask you if it is salty? Is it sweet or not sweet? Okay, I give you a plate of bitter gourd. Question is it sweet or not sweet? You must not say it is bitter. Because that's not my question. Is it sweet or not sweet? Similarly, will it have a terminating decimal expansion or not? So you must say it will not have a terminating decimal expansion. You should not write it has a non-terminating repeating decimal expansion. Did I ask you? No. Or was it asked in the question? No. So answer to the point. Are you from Chennai? No. Seriously, if somebody asks you that question, are you from Chennai? No. Don't say I'm from Trichy. Did they ask you where you're from? Yeah. Are you from Chennai? No, I'm not from Chennai. That's it. Yeah. So does it have a terminating decimal expansion? No, it does not have. So you can see the final statement. Therefore, 11 by 24 will not have a terminating decimal expansion. Don't write it has a non-terminating repeating decimal expansion. Don't write that. That's not asked. Yes or no, children? That's all. Everywhere it's the same thing. Everywhere it's the same thing. So now you understood. Now you understood how to decide if a P by Q has a terminating decimal expansion or not. That's what you just understood. When you're given a fraction without performing the long division, you know how to check if it has a terminating decimal expansion or not. 2-5 terminating. Something other than 2-5 not terminating. Non-terminating repeating. Okay. And what was the other thing was if I smile, I'll forget. Okay, I forgot. I wanted to say something. I forgot. Okay, you got it, children? All of you got it? How to identify if a P by Q has a terminating decimal expansion or not? All of you understood? Without performing the long division. Online students, please acknowledge.
Yes, ma'am.
Yes, ma'am.
Okay, Kritika and Anugraha.
Yes, ma'am.
Okay. Now, insert 5 rational numbers between. Okay. Kritika, how many natural numbers are there between 2 consecutive natural numbers? Okay, let me write. How many? This is for Kritika. How many natural numbers are there between 2 consecutive natural numbers?
Ma'am, infinity rational numbers.
Okay, so between now let me take the natural numbers 3 and 4. Tell me a natural number between 3 and 4. Kritika. Yeah, class. How many natural numbers are there between 2 consecutive natural numbers? Huh? Uncountable. Tell me one.
3.5.
Is that a natural number?
35 by 10 or 7 by 2.
Is that a natural number? Aniruddhan, answer this question. How many natural numbers between 2 consecutive natural numbers?
5.
How many natural numbers are there between 2 consecutive natural numbers? Aniruddhan?
Sorry, ma'am, I do not know.
Oh, very good. I like that. Yes. You're not able to answer this question, right?
Yes, ma'am.
No problem. Yes, children here. Infinitely many. எல்லாரும் infinitely many ஆனா ஒண்ணுமே சொல்ல முடியல. ஒரு நம்பர் சொல்லுங்கம்மா. Tell me one natural number no between 3 and 4.
There is no natural number between 2 consecutive natural numbers.
There is no natural number between 2 consecutive natural numbers. ஏமா நீங்களா இப்ப டேபிள்ல வந்து சப்போசிங் அவ்வளவு ஐட்டம்ஸ் இருக்கு கவுண்ட் பண்றீங்க 3க்கு அப்புறம் 4 தானே சொல்றீங்க 3க்கும் 4க்கும் நடுவுல என்ன நேச்சுரல் நம்பர் இருக்கு இருந்தா நீங்க கவுண்ட் பண்ண மாட்டீங்களா அத 2 consecutive see between 3 and 10 there are some natural numbers but between 2 consecutive natural numbers how many natural numbers are there between 2 consecutive next 9 and 10 க்கு நடுவுல எவ்வளவு natural numbers இருக்கு 9 and 10 க்கு நடுவுல natural number இல்லையே between 2 natural numbers இருக்கும் now like between 5 and 10 yeah 6 7 8 9 there are only 4 not infinitely many between 5 and 10 எவ்வளவு natural numbers இருக்கு 6 7 8 9 நாலு தான் இருக்கு infinitely many கூட கிடையாது இந்த நாலே தான் இருக்கு countable தான் இருக்கு how many natural numbers are there between 5 and 10 between 5 and 10 so 6 7 8 9 நாலு தான் there are 4 natural numbers between 5 and 10 how many natural numbers are there between 2 consecutive natural numbers next natural numbers between 20 and 21 there is no natural number between 20 and 21 yes or no how many whole numbers are there between 2 consecutive whole numbers ரெண்டு whole numberக்கு நடுவுல consecutive whole numbers Anirudh between 2 consecutive whole numbers how many whole numbers
0 ma'am.
there is no whole number right yeah there is no whole number between 2 consecutive whole numbers that's not clear class yes or no நீ ரெண்டுத்துக்கும் ஒரே மாதிரி பாக்குறேன் எனக்கு பயமா இருக்கு did I make you understand or no you got it okay all right how many integers are there between 2 consecutive integers 2 consecutive integers next integers நடுவுல எவ்வளவு integers இருக்கு எல்லாருக்கும் ஆன்சர் தெரியும் ஆனா பயமா இருக்கு சொல்லிட்டு தப்பாச்சுதான் yes online students how many integers between 2 consecutive integers
There is no integers between any two consecutive integers.
there is no integer there is no integer between 2 consecutive integers there is no integer between 2 consecutive integers இப்ப நம்பர் லைன்ல இங்க -3 இருக்கு இங்க -4 இருக்கு -3 க்கு அப்புறம் -4 தான் இதுக்கு நடுவுல நம்பர்ஸ் இருக்கு they are not integers there are many things between -3 and -4 but they are not integers the question is how many integers are there so between 2 consecutive natural numbers no natural number between 2 consecutive whole numbers no whole number between 2 integers no integer but between 2 rationals there are infinitely many rationals அந்த ஆன்சர் எல்லாம் முன்னாடியே சொல்லிட்டோம் அந்த infinitely many ஆன்சர் எல்லாரும் முன்னாடியே சொல்லிட்டோம் அவ்வளவுதான் so between 2 rational numbers there are infinitely many rational numbers now that's what is the question here insert 5 rationals between 0 and 0.5 that now you'll ask me now you explained all this but you're not explaining how do you know that there are many rationals between 2 rationals now we are going to do them what is the question here children insert 5 rational numbers between 0 and 0.1 is the question அப்ப 0 க்கும் 0.1 க்கும் நடுவுல 5 rational numbers insert பண்ண போறோம் there are infinitely many rationals but we are going to insert only 5 there's 5,000 50,000 5 lakh there are many there are many correct but we are going to insert only 5 now why is 0 a rational number did I say it's till 8:45 today hold on 9 you just turn on the fan now, one of you Sahan I'll tell you which switch and Last row, I think the first switch. Last row on that end. Near the regulator. No, very low. Here, here. Okay, so the heading is, the question is insert 5 rational numbers between 0 and 0.1. All right. Now 0 is a rational number because 0 is 0 by 1, 0 by 2. 0 can be written as 0 by 1, 0 by 2. Everything means 0. And what is 0.1? It's a terminating decimal. It's a terminating decimal. So it's a rational number. How do you write 0.1 in the P by Q form? 1 by 10. 1 by 10 is the P by Q form of 0.1. 1 by 10 is the P by Q form of 0.1. Correct? Yeah. So 0.1 is a rational number. So 0 is a rational number. And 0.1 is a terminating decimal. So it's a rational number. And its P by Q form is 1 by 10. 1 by 10. Correct? Okay. So now between these two rationals, we'll have to insert 5 rational numbers. So you can write so many. Now let me start 0 and 0.1. So between these two, 0.01. 0.001. Or you can write 0.02. Just put a, see, now what is 0.1? 0.1 means 0.10, like 10 it is. Okay, so 0.1, 0.2, no, let me, 1 minute. Let me start again. 0 and 0.1, okay. 0.1 is like 0.10, like 10 it is. So this is 0.0, correct? Listen carefully, children. Sometimes, simple things are slightly challenging to explain. Very simple, but yet difficult to explain. So please get it. I'm starting over again. 0 is 0.0 and 0.1 is 0.10. So it's like from, forget the integral part, forget the 0 point. Look at the decimal part. 0 to 10, right? 0 to 10. So let's start writing from there. 0.0. So like you have 2 digits here, no? So like 0, 0. 0.01, 0.02, 0.03. See, try to have the same number of digits after the decimal point. Have the same number of digits after the decimal point. So after the decimal point, 2 digits, 0, 0. After the decimal point, 2 digits, 1, 0. Now start writing from there. After 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 0.05, 0.06, 0.07, 0.08, 0.09, and like 0.10. 10. But we've not come to the end. So like all these numbers lie between these two. Or see here, or 0.000. Take 3 digits. So this will be 0.100. 3 digits. Now this is from 0 to 100. So it will be 0.001. You should maintain 3 digits after the decimal point. Maintain 3 digits after the decimal point. 0. Don't write 0. Okay, so write 0.001. Then 0.002. 0.003. So for somewhere you will come 0.010. That is 10. Then 0.011. 0.012. You should always have 3 digits. So 0.013. Then like that 0.050. 0.060. 0.070. Because 3 digits you should have, no? So 0.0, like you'll get 99 and then 100, 0.100. Either if you, so you keep, widening the space. When you keep widening the space, you can insert. So many numbers we have inserted. Now we'll still widen the space. 0.12, like if you put like this, so it'll be 0.1. How many zeros? 5 digits. See, this is nothing but 0. And this is nothing but 0.1. We are not changing its value. We are not changing the value of 0 and 0.1. Yes or no? Are we changing the value? No. Or we are just widening the space so that we can see that there are infinitely many rationals between these two rationals. So this is 0 point. You should maintain 5 digits, 4 zeros and then 1. 0.000, 4 zeros and 2 like this. So this is 0 and this is 10,000. So you can go up to 9,999. You can keep writing till there. So now do you understand that you can keep widening the space like this and you can insert so many rationals. And that is why we say that there are infinitely many rationals lying between two rational numbers. In fact, whether it is two rationals, two irrationals, one rational and one irrational, whatever it is, when you talk about rationals and irrationals, there are infinitely many lying between them. Whenever, see, when you talk about integers, whole numbers and natural numbers, be careful with the question. When the question uses rational numbers between rationals, irrationals, or a combination of rational and irrational, infinitely many. Between some natural numbers, be careful, read the question carefully. Or between whole numbers, between integers, read the question carefully. But if the question uses how many, rationals or irrationals are there between two rationals, whatever, using only rationals and irrationals, if they ask you how many, infinitely. Am I clear, children, online students? See, multiple questions can be framed. How many rational numbers are there between a rational number and an irrational number? Infinitely many. How many irrational numbers are there between a rational number and an irrational number? Infinitely many. If it is between rationals, irrationals, the answer is infinitely many. All right. Yes. So I have listed a few here. So these presentations I'll share with you. Mostly I'll let you know at the end of the session. I'll tell you what I'll do. So now don't ask me how did you write 0.0. I told you I widened the space and I showed you. So 5 rationals between 0 and 0.1 are 0.01, 0.003, 0.011, this one, and this one. You should always write it in the P by Q form. So 0.01, which is 1 by 100, this one, which is 3 by 1000, this one, which is 1 by 1000, and so on. Now, you should also understand that I've chosen numbers so that we need not reduce them any further. That's why I've chosen numbers like 3, 11, 9, 23. If you write 0.02, no, then again you'll have to simplify. 2 in the denominator, 10, 100,000, you should simplify again. Yeah, okay. So supposing you write 0.02, it's correct. So this will be 2 by 100, which is 1 by 50. 1 by 50. You should put it in the simplest form. You must not stop with 2 by 100. So what I did, purposely I've taken numbers like 0.01, 03, 11, so that you can just write it like this and leave it. You don't have to simplify them. Why waste time simplifying? Correct? Okay. Now, for example, if you write 0.944, sorry, no, not 944, sorry. Supposing you write 0.0988, then it will be what? 988 divided by 1 followed by 4 zeros. Now you'll have to reduce it in the tables of 2 and you'll have to reduce it, right? So that is again time consuming. So don't go for such numbers. So in very simple words, between 0 and 0.1, what to do? Just start with 0.0 and write anything. 0.0 and write anything. Or you write 0.00 and write anything. Yeah. Correct. Just start with, just write 0. Put a 0 safe and write whatever you want, 101, write whatever you want. Because you're safe, you are in with. See, what is 0.01 means it is more than 0, but less than 0.1. It's more than 0, but less than 0.1. Okay, so I told you what is here. You should write the decimals and then put it in the P by Q form. All right. Now between 1.3 and 1.4. So how will you treat 1.3? 1.30 and 1.4 is 1.40. Have the same number of digits after the decimal point. Have the same number of digits after the decimal point. So now read it as 30 and 40. So after 30, what do you write? 31, 32, 33, 34, 35. Okay, all these you can write. Now you can still write in the space. You can write this as this and this. Because see, same number of digits after the decimal point. 1.300 is nothing but 1.3. And this is nothing but 1.4. You're adding zeros, but you're not changing the value. So it's still 1.3 and 1.4. But you've just widened the space. Now it's 300 and 400. So between 300 and 400, so many numbers you have, right? 1.301, 302, 303, 30. Should not write 0 point here. 1 point. Don't write 0 point. 1.301, 1.302, 1.303. Like that, you can go up to 1.399, 399. Okay, so starting from 1.301, you can go up to 1.399. Then it's 400. Otherwise, still widen the space. 1.3000. You cannot read it as 3000, 3000, but 1.4000. So between 3000 and 4000, 3001, 3002, 3003. So like this, you can write many. I have written a few here. So like that, I've widened the space and I've written it. Oh, sorry. Is that fine, children? Now this you must have seen last year itself, inserting. So you bring them to the same denominator. You first bring them to the same denominator, right? 3 by 8 and 2 by 5. Bring them to the same denominator. So how do you bring them to the same denominator? LCM is 40. So into 5 into 5. So it becomes 15 by 40. And this one is into 8 into 8. It's 16 by 40. Correct? So now 15 by 40 and 16 by 40, there is no space in the numerator. There's no space in the numerator. Because 15 by 40, 16 by 40. So you can widen the space by multiplying it by any number, like 100 and 100. Any number you can multiply. So multiply this also by 100. So what do you get? You get 1500 by 4000. And here 1600 by 4000. So now you can write 1501 by 4000, 1502 by 4000, 1503 by 4000. All these are rational numbers between 3 by 8 and 2 by 5. So first step is you should bring them to the same denominator using the concept of LCM. Using the concept of LCM, bring them to the same denominator. And then if there is no space in the numerator, like 15 by 40, 16 by 40, it comes immediately after 15 by 40, right? 16 by 40. There is no space in the numerator. So widen the space. So now it is 1500 in the numerator and 1600 in the numerator. Lot of space we have. Now insert. What I have done here, any number you can multiply. I told you any number. Just to widen the space. So first using the concept of LCM, 15 by 40 and 16 by 40. Then I've multiplied 15 by 40 with 6 and 16 by 40 also with 6. So it becomes 90. 15 into 6 is 90. 40 into 6 is 240. 16 6 are 96. 46 are 240. Now we have widened the space in the numerator. 90 and 96. Now insert the numbers 91, 92, 93, 94, 95. And what I've done is I've also, now when you write 92 by 240, you can simplify. So that simplified form I've written here. Then when you write 93 by 240, you can simplify. So that simplified form here. Understand? 94 by 240, you can simplify. So that one here. Whenever it is possible, you should simplify. So again, this one, see, 1 minute. See here, can you see 91 by 240, 92 by 240, 93 by 240, 94 by 240, 95 by 240. These are 5 rationals between these two. Now this 92 by 240, you can simplify, which is this. This one can be simplified. This one also can be, that simplified version, I've written it immediately. That's all it is. So when you have to insert rationals between two rationals, what you do? First, they have different denominators, 8 and 5. So use LCM and bring them to the same denominator, which is the LCM 40. That's his first step. Then if you look at the numerator, 15 and 16, no space. So widen the space. How? By multiplying like this. Any number you can multiply. You can multiply by 10 also. 10 and 10 here, 10 and 10 here. So the space in the numerator will widen and then you insert. See, now it becomes denominator is the same 240. The numerator becomes 90 and 96. So between this you have 91, 92, 93. So 91 by 240, 92 by 240, 93 by 240 and so on. All right. Okay, it's time. We'll have to wind up. So class, we'll quickly recap. So what did we see first? Natural numbers, whole numbers, integers, and all these are rational numbers. On the other side, you have irrational numbers. Rationals and irrationals put together form real numbers. Every real number has a unique position on the number line. You can represent every rational number on the number line. You can represent every irrational number on the number line. Rational numbers have a terminating decimal expansion or a non-terminating repeating decimal expansion. Irrational numbers, they don't have a P by Q form and they have a non-terminating, non-repeating decimal expansion. Correct? And if a P by Q has a terminating decimal expansion, without actually performing the long division, you can use that technique to check if it has a terminating decimal expansion. Correct? You put it in the simplest form, take up the denominator, express the denominator as a product of primes, and if the primes are only 2 or 5, terminating decimal expansion. Anything other than 2 or 5, non-terminating repeating. Correct? And then towards the end of the session, we saw how to insert rationals between two rationals. So that's all we saw today. All right. It is kind of dry, when we get started with the, real numbers. Maybe it was interesting, but it can be, you can feel it's a little dry too, but it's just okay. But once you get started, once we kind of, maybe the next class onwards, it will become interesting, meaning the concept will be more interesting. You'll start working. So don't think every class I'll just lecture like this and you will not write. You will write. This being the first session, and since they are very basic, I thought I can teach you more than making you write and spend time. This I can even share it with you and you can complete this at home, right? So every time I can do this, this is what will happen in the class. I'll lecture and then I'll share the notes with you. We'll complete it at home. If you have to work it in the class, yes, you will be made to work in the class. All right. All right, children. And one more thing is, see, I moved to the center only last December. Okay. And December, Jan, Feb, I didn't feel much. But now I realize I cannot sit here without the AC. So maybe meaning now tomorrow or sometime I have to now make some arrangements to get the air conditioners installed. If that work is in progress, we'll have only online class till I separate the classroom because I cannot sit here. Nor can you all sit. So because when I came in December, Jan, Feb, it was quite fine. We didn't even use the AC, but now I'm not able to sit in the class. I'm just not able to sit in the class. So I need to, I don't know, 1 or 2, I have to get it installed. So if that work is going to be in progress, we cannot have the physical sessions. So you have to manage it online. Once the work is done, we'll resume the physical classes. Is that understood, children? Okay. All right, online students. So that's it for today's session. Thank you so much. Good night. You may leave the call.
Thank you, ma'am.
Thank you. Good night.
Thank you, ma'am.
Thank you. Good night. Thank you, children. Good night.